Hello and welcome. My name is Shaun Sanyal and I'm a Senior Database Specialist Solutions Architect here at AWS. In today's session, we'll cover a few design patterns for achieving high availability and disaster recovery for our Amazon Aurora Global Database offering. We do have a packed agenda, so let's dive right in. So I would like to kick things off with a quick recap of Amazon Aurora. Then we'll do a quick overview of Aurora Global Database. We'll then dive right into the HA and the DR use cases as well as design patterns. Then we'll take a look at a few custom solutions that our team of database specialist solutions architects have put together for common customer challenges. And finally, we'll wrap up with some resources to continue your journey with Amazon Aurora Global Databases. So let's start with a quick recap of Amazon Aurora. So with Aurora, we've done things a bit differently. We've decoupled the compute and the storage layers, and in Aurora, the logging and the storage layer has been moved into a multi-tenant, purpose-built, distributed storage system, which is separate from the SQL, transactions, and caching layers handled at the compute layer. Now, with that background, let's double-click a little bit on the storage architecture. The shared storage volume in Aurora gets striped across hundreds of storage nodes over 3 availability zones. Now, if you're not familiar with what an availability zone is, an availability zone is a logical data center in a region available for use by any AWS customer. Each zone in a region has redundant and separate power, networking, and connectivity to reduce the likelihood of 2 zones failing simultaneously. In Aurora, we replicate the data 6 ways, and each page is replicated across 3 availability zones with 2 copies in each availability zone. The green, the red, and the white boxes here in the diagram on your right represent the 2 copies on each AZ of these storage nodes. Why did we build it this way? Well, this architecture serves 2 distinct advantages. First, it gives the additional durability to the storage layer since data is backed up to S3, which provides 11 nines of durability. And second, it helps us survive failure of an entire AZ plus an additional failed node. Lastly, it's important to point out that data is written in 10 gig protection groups, growing automatically when needed up to a maximum size of 128 terabytes. Now let's talk a little bit about global databases. So Aurora Global Database enables 2 primary use cases. The first use case is supporting a disaster recovery solution that can handle a full regional failure with a low recovery point objective and a low recovery time objective while minimizing impact to your database cluster. With Aurora Global Database, you can typically achieve an RPO of less than 5 seconds and an RTO of less than 1 minute in most cases. The second use case for Aurora Global Database is providing read-only copies of an Aurora cluster in up to 5 remote regions to serve users closer to those regions. This, of course, provides users in those remote regions with lower latency reads than having to connect to the further away primary region. I would like to point out that the number 1 vertical for Aurora Global Database today is financial services customers. If you are a financial services customer, or if you do have a customer who is from the financial services background, plan for a conversation with your stakeholders about Aurora Global Database to achieve DR, region resiliency, as well as compliance. The number 2 use case is customers with cross-region end users and needing region local latencies for local read use cases. You can read more about how a company called Smart News uses their Aurora Global Database architecture to serve their worldwide end users in the link on your screen. Moving on, in this example, US East is the primary region and EU West is the secondary region. This is the first use case for Aurora Global Database. In case of a disaster in US East, we give you the provision to failover to EU West to ensure a fast cross-region DR solution. This is the second use case for our global databases. And in this example, we have US East as a primary region and 3 more secondary regions. In this case, we have our reads horizontally scaled across US West, EU West, AP Southeast, and typically the replication lag across these regions is less than 1 second. So the architecture itself for Amazon Aurora Global Database is based on a physical log-based asynchronous replication topology, which is different than the logical replication that most of us would be familiar with in the open source community. We use an optimized replication service for data transport across the AWS backbone network with multiple encrypted connections to reduce jitter. And note that we can have up to 90 read replicas in up to 5 secondary regions in our global database cluster, which is pretty huge. This is how it looks in action. So on the diagram, you'll see region A with 3 availability zones with your read-write node in availability zone 3 and 2 read-only nodes or read replicas in availability zone 1 and 2 respectively with a shared storage volume. Now with global database, we have region B. This is completely different region in a different geographic location across the world. And here we have the same architecture, but we have just one read-only node with a shared storage volume. Note that here on the region A side, we have a fleet of replication servers, which interacts with a fleet of replication agents in the other region. Now, when you send a write from your read-write node, it of course goes to the Aurora storage and the read-only nodes in parallel. And from the Aurora storage node to the replication server, and also from the replication server to the replication agent in the other region, from where it gets replicated to the Aurora storage layer and the read-only node. Now, in the case of multiple read-only nodes, you can have up to 15 in the secondary region that can again attach to your Aurora storage, which is the same storage, and read and horizontally scale your read architecture and making it more highly available in the other region. Now, in the rare event of a regional failure, we give you the provision to promote a read-only node to a read-write node in the secondary region. And there are a couple of ways to do it. And depending on the way you choose to do it, you can have the same topology in the reverse order with a fully functional global database topology established in the other region, region B in this case as your new primary, and your original region, region A in this case as your new secondary region. In this case, of course, we are able to achieve a very high throughput of up to 200,000 writes per second with negligible performance impact. Also, since the fact that this is physical storage-based asynchronous replication, we still see a lag, but this is significantly low, typically less than a second cross-country under heavy load. And in the rare event of a regional failure, we are able to promote a secondary region to a primary and start serving full read and write capabilities in under a minute in most cases in the secondary region. Now let's dive into some of the use cases for global databases. The first of them being distributed multi-region apps want region local access for read or write. With the read replica write forwarding feature of Aurora Global Database, performing writes in remote regions becomes much easier. The primary use case is to simplify application development. Write forwarding works by accepting a read-write statement from an application in a secondary region's read replica. In this example, assume that the application is performing its writes in the secondary EU West region. Then in this configuration, Aurora forwards those write operations to your primary regions cluster in US East, where the write statement is then executed on the primary instance. Multiple consistency modes are provided, which allows you to balance consistency and performance. So let's take a look at it in more detail. In this example, we have our primary region in Ohio, which is connected to one of our applications, let's say app A, and we have 3 more secondary regions in Oregon, Northern Virginia, and Ireland. And one of our other applications, app B, is connected to the Oregon region. Now assume that application B wants to do some writes in the Oregon region, which is our secondary region, through the read replica. What will happen is first the application writes to the read replica in Oregon. Next, those writes are then forwarded to Ohio, which is our primary region. Third, the Ohio region, which is our primary region, acknowledges and commits the transaction. And lastly, replicates the update to all secondary regions. So any results from executing these statements, including warnings and errors, are always returned to the remote instance and then to the application. This entire process is also transparent to the application. So you need to only enable write forwarding for the cluster and set the consistency mode for each session where you want to perform a write. That's all that you need to take care of as an end user. So overall, write forwarding gives us 4 key benefits. First, it's a fully managed solution. So writes issued at a remote cluster are transparently forwarded to the primary cluster using secure cross-region communication channels. Second, there are no replication conflicts. Because all writes are applied by the primary cluster, replication-related update conflicts do not occur. Third, it's simple. So you can issue writes to the remote cluster followed by reads that will observe the previous writes. And finally, the fourth benefit is it's very flexible. So you can choose among several read consistency levels to balance consistency and performance. We offer 3 consistency levels. So we have the eventual, the session, and the global consistency levels. And you can read more about these consistency levels in our AWS documentation. Now let's talk about our next use case, customers who want to save costs on DR. Now it's also possible for Aurora Global Database to run headless in the secondary AWS region. This means that the secondary region will not have a running database instance and just the Aurora storage layer. Aurora will replicate log records to Aurora storage in the secondary region to keep it in sync. And you can always add a replica before failing over whenever you need it. So this way you save compute costs at the expense of a higher RTO, because although short, it takes that additional time to create that compute node when you want to fail over to the secondary region. We also recommend you to monitor the replication lag in the other region using CloudWatch and then fail over when the lag is at a minimum. Now let's look at the next use case, customers who want to cap the maximum RPO loss to a limit. So within Aurora Postgres-based global database, you can manage the RPO for your global database by using a parameter called global DB RPO. Now this parameter exists in the DB parameter group, and this represents the maximum amount of data that can be lost in the event of an outage. When you set an RPO for your Aurora Postgres-based global database, Aurora monitors the RPO lag time of all secondary clusters to make sure that at least one secondary cluster stays within the target RPO window. The RPO is used when your database resumes operations in a new AWS region after a failover. So in this case, Aurora will first commit the transaction if at least one secondary database cluster has an RPO lag time less than the RPO, or it will block the transaction if all secondary database clusters have RPO lag times that are larger than the target RPO. It also logs the event to the Postgres log file and emits wait events that show the block sessions in Performance Insights. In other words, if all secondary clusters are behind the target RPO, Aurora will pause the transactions on the primary cluster at least until one of the secondary clusters catches up. And these paused transactions are resumed and committed as soon as the lag time of at least one of the secondary database clusters becomes less than the target RPO. The result is that no transactions can commit until the RPO is fully met. So with managed RPO, as we saw in the previous slide, you define the maximum RPO that you allow using the DB parameter. If the RPO lag in all secondary regions exceeds that limit, Aurora pauses writes until at least one secondary region catches up. Now let's see an example where we set RPO to 20 seconds. So in this example, we have our Ohio as a primary region and two other secondary regions, Northern Virginia and Ireland, where the RPO lag is less than the RPO that we set, which is 0.4 seconds in each of these secondary regions. So it's within the limit. Now, as we proceed forward in time, Northern Virginia sees a RPO lag of 22 seconds, which is more than the RPO metric that we set of 20 seconds. However, lag is still okay in Ireland. So the writes continue to happen in the primary region in Ohio. Now, as we move further forward in time, both the secondary regions, Northern Virginia and Ireland, see a lag which has exceeded the limit that we set of 20 seconds in both these regions. Now, in this case, what will happen is Aurora will pause the traffic, the write traffic in the primary region, until at least one of the secondary regions has an RPO lag of less than the limit that we set. So in this case, Ireland is back after a point in time to 15 seconds, which is less than 20 seconds, and hence the writes have resumed in the Ohio region. The next use case is for customers who want to meet DR test regulatory compliance requirements. So the primary use case here is by using this feature, you can relocate the primary cluster of your Aurora global database to an entirely different region on a routine basis. And being able to demonstrate this capability with your production systems is a legal requirement for a lot of companies like government agencies, financial institutions, and many other regulated industries. This feature is intended for controlled environments such as DR testing scenarios, operational maintenance, and other planned operational procedures. As an example, say a financial institution headquartered in New York has branch offices located in San Francisco, in the UK, and in Europe. The organization's core business applications use an Aurora global database. Its primary cluster runs in the US East region, with secondary clusters running in the US West and the EU West regions. Every quarter, it relocates the primary cluster from the primary AWS region to the secondary region designated for that rotation. Now, not every organization needs to rotate their Aurora global database's primary cluster on a regular basis. However, the ability to do so during an audit by regulators is a key requirement to meeting DR requirements for these companies. So we recommend using managed plan failover for such organization as a best practice for DR. This not only ensures that your procedures are complete and accurate, but more importantly, that staff are trained to perform a DR failover before it really happens. Now let's see an example how this happens in action. So we have a similar setup to the previous example. We have our primary region in Ohio and our secondary regions in Northern Virginia and Ireland respectively. So in this example, we will promote Northern Virginia to primary, which is one of our secondary regions. So through the console or the API or the SDK, we click to promote Northern Virginia first. What happens after that is Ohio writes are stopped. The secondary regions catches up. So in this case, Northern Virginia and Ireland catch up. Northern Virginia becomes the new primary, and hence the writes are now available in Northern Virginia. Finally, point your application to the new endpoint in Northern Virginia in your primary cluster, and you're good to go. So in this case, there is essentially no data loss because writes are stopped until your new primary catches up. The secondary regions are always up to speed, up to date on whatever data was written to your primary region. And the RTO is actually directly proportional to your Aurora Global DB replication lag metric value, which is available in CloudWatch for all the secondaries. Now let's take a look at our next use case, customers who need to recover rapidly on region failure. On very rare occasions, your Aurora Global database might experience an unexpected outage in its primary AWS region. If this happens, your primary Aurora database cluster and its writer node aren't available, and the replication between the primary cluster and the secondary ceases. To minimize downtime or RTO and data loss or RPO, you can work quickly to perform a cross-region failover and reconstruct your Aurora global database topology. We recommend that you understand this process before using it. So having a plan ready to quickly proceed at the first sign of a region-wide issue is the first step. Be ready to identify the secondary region with the least lag time. Use Amazon CloudWatch regularly to track lag times for the secondary clusters, and make sure that application writes are sent to the correct Aurora database cluster before, during, and after making changes such as these to avoid data inconsistencies among the database clusters in the Aurora global database, thereby avoiding split brain issues. Now, our next use case is for customers who want to automate tasks on DR failover to reduce RTO. Now, building on the foundations from our previous slides, I wanted to point out a few custom solutions that our team of specialist solution architects have built to solve some common customer challenges. Two of these are highlighted here. So, disaster recovery in itself is an important part of resiliency strategy and concerns how a workload responds when a disaster strikes. The most common pattern to have as a disaster recovery solution in AWS is to build a multi-region application architecture, including a backend data store. Cross-region failover for typical online transaction processing databases often requires a clear strategy, resources, and manual actions related to switching database endpoints. Managing all of these tasks can be challenging to the overall DR solution. And in the case of a real disaster, the Aurora cluster in the secondary region needs to be promoted to have these right capabilities. In order to do that, it needs to be removed from the global database cluster, and the secondary regions cluster becomes what we call as a standalone cluster in that process. Now, as the secondary regions cluster becomes available, we get new reader and writer endpoints. And these endpoints need to be changed in the application configuration to point to the correct database. All of these tasks can be error prone and time consuming if done manually. So in both of these blog posts, we provide an approach for scripting your Aurora failover tasks and automating the process of managing global database endpoints after a failover. I would highly recommend going through the links on your screen to learn more about these custom solutions. Finally, our last use case is for customers who want to automate provisioning and failover for their Aurora global databases. Now, another common challenge shared by our customers is that provisioning and managing a multi-region infrastructure by hand is often time-consuming, error-prone, and can lead to unintended consequences upon switching your primary region. So Terraform by HashiCorp is an AWS partner, and they provide infrastructure as code tools similar to AWS CloudFormation that allow you to create, update, and version your AWS infrastructure. Enterprises rely on Terraform to create and manage their cloud infrastructure in a repeatable and predictable manner. It's pretty widely used among a lot of our AWS customers. Now, here at AWS, we have something called quick starts, which are basically automated reference deployments built by AWS solutions architects and AWS partners. Now, amongst many other quick starts, we also have a quick start for Amazon Aurora to provision and manage Aurora global databases across multiple AWS regions in Terraform. So again, highly recommend going to the link on your screen here to learn more and deploy these solutions. Finally, to wrap up, here are some resources which I hope will be helpful. And we'll also share these in the description box below to continue your journey with Amazon Aurora global databases. So that's all I had for you today. Hope you enjoyed this video and do stay tuned for the next one. Thank you for listening, and as always, happy cloud computing from all of us here at AWS.